Okay, so it's 4:15. So let's start the last talk of the day. We have Professor Julien Vidal from Sorbonne University in Paris talking about string nets at finite temperature.
Thanks a lot. Thank you for still being awake. It's already pretty late. Thank you, Subro, for inviting me in this very nice place. I'm really happy to be here and to have this opportunity to present the very recent results we've been obtaining these last 2 years in collaboration with Jean-Noël Fuchs and our PhD student Anna Ritzling, as well as Steve Simon from Oxford. And more recently, we are also working with Benoît Dussault in LPTHE in Paris on the very similar issue. So today, what I want to explain to you is how to understand the property of topologically ordered system at finite temperature. What can we do? What are we able to understand? And what does it mean, basically? So let me first remind you a very simple set of things about topological quantum order for those of you who might not be familiar. And don't hesitate to interrupt this if needed. So I think it's fair to say that this whole field really begins in the 70s with this very famous paper by Linus and Miriam, who understood that in 2 dimensions, so in flat land, it was possible to have non-trivial quantum statistics. So this morning there was this talk by Yuval. You've heard about anyons. I will try to precise a bit what it means in this context. So just to say that this name of this weird object has been given by Frank Wilczek in 1981. And it simply means that you can have any exchange phase statistics. And right after, in 82, the discovery of fractional quantum Hall effect really start to develop the whole field. And many people, as you know, propose some wave function to describe these new phases of matter. So, of course, Bob Laughlin's. And then more sophisticated anyons have also been proposed, like non-abelian anyons. And there has been all this bunch of variational wave functions that have been proposed to understand that. And I think this was really the very origin of topological quantum order. But at that time, people were happy with that and nothing really weird happened. And then in 1986, with the discovery of high-TC superconductors, people again proposed to describe those very complicated systems in terms of spin liquids and chiral spin liquids, especially Kallmeyer, Laughlin, and all these ideas coming from this celebrated RVB states from Anderson and coworkers. And then Chaogang Wen and others realized that some of those states, some of those chiral spin liquids, has exactly the same symmetries, but were different. So basically it means that those states could not be distinguished with respect to symmetries. And this really gave rise to this notion of topological quantum order. So for those of you who are interested, you can have a look at this nice review paper by Chaogang, who explains all those things. And then in the 90s, following these very interesting ideas, there has been many systems which have been proposed by various people. So of course the celebrated Moore-Reid wave function for fractional quantum Hall effects, also the Z2 quantum spin liquid by Reid, Sachdev, and Chaogang Wen. And later on, in the late 90s, Alexei Kitaev understood that those states of matter, which have some very special properties, could be used for topological quantum computation. So there is this famous paper about the Turing code, which has attracted much attention. And one of the main reasons for that is that those phases of matter, which are topologically ordered, are essentially protected against perturbation. Okay, so if you have a system which is an anyonic system, if you want to encode some information, if you want to perform some quantum computation with it, it's protected against some small errors, small perturbation. And we will try to quantify that and to explain to you how it works, especially when this perturbation is simply the temperature. And just to conclude this very short story, these anyons have been proposed almost 40 years ago, so by Linus and Miriam. And but the genuine property of anyon, which are basically these non-trivial statistics, have only been observed in 2020 in this set of 2 experiments. And that's one more example of the things where theory can arise before experiments. But and now, since this groundbreaking facts, many other people are using the same setup and trying to measure non-abelian statistics and stuff like that. For those of you who might not be in the condensed matter field, it's also important to keep in mind that most of the things that I will discuss today are related to completely different fields in high energy physics, in math theory. I listed here the most important ones. So obviously, the topological contour model is related to lattice gauge theory's picture. Everything I will show you is some sort of extension of this lattice gauge theory, which have been proposed in the 70s. Many results that we have been using to derive the main results that I will show also comes from conformal field theory, but to be more precise, it's essentially from topological quantum field theory. And there are also some connections in mathematics with knot theory and many other domains. Okay, so what are the key notions that you should keep in mind when dealing with topological quantum order? It's essentially that the systems are two-dimensional. I explained to you that we are living in flatland now for the next 40 minutes. We are also dealing with interacting systems, so we need both dimensionality and interaction to have NION. And to make things short, I think it's fair to say that topological quantum order simply characterizes NION theory. So if you know everything about NION, you will know everything about topological quantum order. You don't have to learn anything else. And usually when you talk about NION theory or topologically ordered phases, you have in mind that one of the main properties that the ground state degeneracy of the system you're interested in simply depends on the topology of the system. Okay, so again, I will show a couple of examples. And this important properties is actually directly encoded in the fact that the proper excitation in the systems are NION. So most of you know that NIONs are some non-local properties, and this non-locality is directly responsible for this topology-dependent ground state degeneracy. And also, it also means that if you take two ground states, if you compute the matrix elements of any local or quasi-local operator, in the sense that it does not cover a finite fraction of the system, so something you measure a sort of magnetization for a spin system or something like that, it will always be a diagonal in the two indices, alpha and beta, for the two different ground states, up to some corrections whose behavior might be usually exponential, but you can also have some more fancy finite size corrections. So you also have some other parameters which are non-local, and this is also directly associated to the fact that NIONs should be thought of excitation with strings. I will show you how it works. We also have long-range entanglement, but all these very specific features are just the same side of just different side of the same coin. Sorry. Okay, so I already explained that those systems are robust against perturbation at zero temperature, but today will be essentially interesting in understanding what happens when we start to warm up a topologically ordered phase. Right. Okay, so what should be known for non-expert in NION theories is that an NION series for a theoretician is essentially described by a finite set of objects. These objects will be the NIONs of the theory. These objects will obey some fusion rules, which basically tells you what happens when you want to bring these two NIONs together. How do they behave? What kind of state can they give? You also have to specify the braiding rules, which will tell you what happens when you start to braid one object around the other. Another important quantity is the chiral central charge, which is also directly associated to the fusion and braiding rules. And this set of S matrix, which characterizes the fusion and the braiding, and the T matrix, which is essentially the self-twist. Basically, for fermions, you expect this minus sign, for boson the plus sign. And the chiral central charge, these three quantities, S, T, C, almost fully characterize the NION theory. Yes? A composite system of two NIONs. Yes. The braiding rules, it tells you what happens if you take one NION and if you braid it around another NION. And the T matrix is what happens when you take one NION and you braid it around itself. Okay, so the T stands for twist, and S for scattering matrix because it comes from high energy physics, but that's basically it. And among all possible anion theory that you can meet in literature, usually you distinguish abelian anions as the one discussed by Yuval this morning, and that you can meet in the simple fractional quantum Hall states with nu equal 1/3, for instance. Versus non-abelian anions. So I'm not sure I will have time to explain that. If you have some question, I could explain to you the main difference, but these are just some names, and it's directly related to the nature of the fusion rules. And basically, you have two different types of topological phases, the one which are chiral and the one which are non-chiral. And today I will essentially focus on achiral phases. And just to say that a complete classification of all possible anion theory is still some work under progress. And the most recent results that I know are given in this archive paper. And they classify all possible anion theory, which contains less than 11 types of anions. So it's a complicated problem. It's not complete yet, and it will certainly never be complete because the algorithm is still very, very difficult. And you can always think about a very large number of objects in your system. But you should simply keep in mind that there is a finite set of anion when you want to describe. So for instance, for nu equal 1/3, you have 3 types of anion. For Fibonacci anions, you have 2 types of anion and all. Right. Okay, so today I will try to explain to you what is contained in this picture, which is a pictorial representation of the stringnet model given by Chaogong Wen. So don't be afraid. I don't speak Chinese, so some of you knows how to describe. I just know that it's a poetry because it's given on the Chaogong website. But this is his view of the stringnet model that he has been proposing with Michael Levin in 2005. And what is important in this picture is to see that you have a sort of noodle soup with some noodle which can have different colors. They can connect according to different rules, and that's basically all you need to know to understand what are stringnets. Obviously, I'm cheating a bit, but let's see. Okay, so now I'm going to introduce this Levin-Wen model, the stringnet model. Then I will tell you the results and the way to compute the spectrum degeneracy of each energy level, because what is nice is in this kind of model is that the energy spectrum is very simple. It's like an equidistant spectrum, like a harmonic oscillator, if you wish. But what is a bit more complicated to compute is the degeneracy of the energy level. And once you have both the spectrum and the degeneracy, it's almost completely trivial to compute the partition function and any finite temperature correlation function like Wilson loops or things like that. Okay, so Levin-Wen model. So the Levin-Wen stringnet model is a very simple model, which is usually defined on trivalent graphs. So you can think about honeycomb model in its original formulation. And I will call NV the number of vertices on my lattice and NP the number of plaquettes. And how does it work? So you need only one set of ingredients to define the model. You need an input theory, which is given by what is called a unitary fusion category. Okay, so I will call it C. And for people who have never heard, who do not want to hear about category theories, there are many. You should simply think that it's again given by a set of objects. You can think about spin half, for instance, if you wish, or spin 1 or spin whatever you wish. Sometimes it's more complicated than a spin. It can be some group elements and many other things. In the literature, these objects, which is the usual name for the things belonging to a category, can also be called strings or labels or charge or super selection sector, whatever you wish. And to define the model, we need this set of objects. So this category is given by this set of objects and the fusion rules, as I explained, to which these objects obey to. Okay, and the fusion rules directly also give you access to what is called the quantum dimensions, which are just some real numbers obeying exactly the same equation as the fusion rules. Okay, so I will not need anything else for today. And what is really nice in this construction of the Levin-Wen model is that, so you start from this category C. Okay, so you have C with its subject and all that. And at the end of the day, the emerging theory is given by another category, which is called the Drinfeld center of the category C. And the Levin-Wen model Hamiltonian is just a way to start from the microscopic degrees of freedom given by C and the excitation given by the Drinfeld center of C. Okay? So for people who are familiar with IISc quantum double or tori code or things like this should be seen as a natural extension of this kind of things, in the sense that in IISc quantum double, you start from a group, and using the IISc quantum double Hamiltonian, you find at the end of the day the double of the group as the anionic excitation, anionic theory describing the system. Okay. So this is the input theory, that the output, and now we can try to understand what are the main properties. And I just first wanted to mention that this should be seen as a toolbox to generate any possible achiral topological phase. Because for people who knows a bit about Drinfeld center and category theory, the Drinfeld centers of a given unitary fusion categories has a zeroth central charge. So all the phases that we can build with this Levin-Wen model will be achiral phases. And what is interesting is that you can build all of them. Okay, so if you pick up the proper initial category, you can engineer any achiral topological phase. Okay, so I just give you here a brief sketch of all possible unitary fusion category that we can start from. So some of them will have commutative fusion rules, some of them non-commutative fusion. Once you have commutative fusion rules, your category can be braided, can be non-braided. And when it's braided, it can be modular, non-modular. So this is a realm of unitary fusion category. Don't worry if you don't know anything about it. The only thing you have to keep in mind is that the extension of the Levin-Wen model, which has been proposed later on by Lin, Bernal, and Levin, allows you to consider as an input category any fusion category. So you can pick up any of them, and then you will work with the Drinfeld center of this category. Right. So as I explained at the very beginning, the degrees of freedom, the microscopic degrees of freedom of the model will be the object of the input category C. They are defined on the links of the graph that I do consider. So it has to be trivalent. And what is important to keep in mind is that the Hilbert space of my system is defined as a set of all configuration respecting the fusion rules at each vertices. So what does it mean? It means that if I have vertices on my lattice, so it's a trivalent lattice, I have my degrees of freedom which lives on the link, okay? And what means this sentence here? It means that a state will be allowed if I have one object in a state A here, if I have one object in a state B here, then this one has to be in a state C, which belongs to the fusion rules of A and B. Okay, is that clear? Okay. So one simple example that you might have heard about is you take as fusion categories a Fibonacci category. It contains two objects, usually called 1 and tau. I wrote here the fusion rules. So you have 1 cross 1 gives 1 cross tau gives tau, and tau cross tau gives 1 plus tau. This is why it's called Fibonacci. And then each vertices, if I draw a blue line for the state 1 and a yellow one for the state tau, these are the 5 possible states at each given vertices. Okay, so you see that, for instance, one of them cannot appear because, for instance, if I would have 1 times 1, well, blue, blue, there is no vertices with blue, blue, yellow because 1 cross 1 only gives 1. Okay, so now you take your entire graph, and all possible states in the Hilbert space are the states. Any coloring of the graph fulfilling these fusion rules will be one state in my Hilbert space. So you can compute the total dimension of the Hilbert space. It's given by this formula. Believe me, it's an integer because it's a dimension of the Hilbert space. And phi here simply denotes the golden ratio. And this is obviously only for Fibonacci. Sorry? Any even NV, but NV has to be even because I essentially consider compact surface and trivalent graph. So there are additional constraints, but yeah, essentially for any even NV, it's an integer. ¿Cómo? So the thing is the following. So the starting point, you just give me your unitary fusion category, and this category is defined with its object and its fusion rules. So it's part of the initial rules of the game. Okay? So yeah, so basically, well, I could give you other simple examples like Z2 category, like things like that. And you give me the fusion rules from the very beginning. So it's given. Let's say it like that. Okay? Okay, and then once I have my Hilbert space, I can ask what is the Hamiltonian of the system. So it's given by the sum over all plaquettes. So the operator PP is a projectors which acts only on the plaquettes of my graph. Okay, so I have a trivalent graph like honeycomb, and the object PP, this projector acts onto the plaquette. And what is important here, so I don't give you the microscopic action of PP. Sometimes it's written in terms of F symbols and stuff like that. I don't want to enter too much into details. But the only thing which is really important here is to keep in mind that this Hamiltonian is a sum of local commuting projectors. Okay, so the PPs are projectors operators, so they square to themselves. And they should be seen in this system as being the projector onto the vacuum in the plaquette P. So what does it mean? It means that the vacuum or the ground state of my Hamiltonian will be obtained when I have essentially nothing in my plaquette. And in this case, the projector PP will have eigenvalue +1. And each excitation in the system will change the value of PP. It will go from 1 to 0. And it can be interpreted as having one excitation inside my plaquette P. Okay, is that clear? No. It's well, if you wish, yes. It's a direct sum. So I have projector acting on plaquette 1, plaquette 2, plaquette 3. So that's basically. So you can see directly that in such a situation, the energy spectrum is completely trivial. So when I have no excitation, let's say Q equals 0, the ground state is given by minus the number of plaquettes because PP equals +1 in each plaquette. Okay, and as soon as I switch one PP from 1 to 0. I have excitation 1, 2, 3, so it's an equidistant spectrum. But what is this? What this? This black. Oh, this is a commutator. No, I think this plaquette is what? Plaquette physically what does it mean? I don't see what you mean. The vacuum in the plaquette P. The plaquette P. What is a plaquette? Yeah. Okay, sorry. It's a plaquette. So you have a graph. Okay, so whatever you wish, it has to be trivalent, but you can take. So this is a plaquette. This is the, so here I have one plaquette 1, plaquette 2, plaquette 3, plaquette 4. So it's a closed surface made of elementary links on my graph. So you are saying like a projector on that plaquette is commuting with the other? Yes, exactly. So is it some sense capture the bottom of that locality? Doing something here I cannot do instantaneously. Yes, so somehow you may even argue that this is not even quantum mechanical. Okay, I have a set of commuting variables. I can take them to value +1, -1. Okay, but what will be non-trivial in the game is the degeneracy of this model. Yeah, sorry, I didn't understand what you were saying. So for people who knows a bit about the toric code proposed by Kitaya, the celebrated Z2 toric code, which is useful for quantum memories and things like this. So you have these two terms, usually the plaquette term and the vertex term. And here you can see that we have only the plaquette terms, indeed, the PP operator, which is a counterpart of BP. And usually in the toric code, you also have the vertex term, but the fact that I impose the fusion rules to be satisfied at each vertices is like saying that I have no charge excitation in the toric code, okay? So it's like saying I'm only working in a restricted subspace where AV equals +1 at each vertices. So we can also say that it's a pure gauge theory. I have no matter, I have no excitation at vertices. Well, there are several ways of saying this. And actually, this toric code is just a special case of the stringnet Hamiltonian, where I have no charge excitation and where I pick up as initial category Vex Z2, which gives me this category. So it's not the same as Fibonacci. It's different fusion rules. It's slightly easier, but that's the way it works. Okay. So now, spectrum degeneracy. So as I explained, the energy spectrum is completely trivial. It's a harmonic oscillator, equidistant spectrum. But now we want to know what is the degeneracy of the ground state. So luckily enough, long time ago, well, 40 years ago, people from topological quantum field theory consider similar issue. Also, it has apparently nothing to do. But most of the results that we have been using here, that I will briefly flash, are contained actually in these two papers, the famous paper by Verlinde and by Moore and Seiberg in 88 and 89, where they show that when you have a system which we would say today, which is topologically ordered, so when you have a topological phase, the ground state degeneracy is given by this expression. So what do we have in this expression? We have several ingredients. So we have a sum, which is performed over all objects of the Drinfeld center of C. So remember, the proper excitation of my systems are given by this set and this category. Okay, so A is one object of this category. And here we simply have a ratio of two quantities. The first one is a quantum dimension dA of the anion A. Okay, I told you that the quantum dimension is an integer number which is directly given from the fusion rules. So this is only dependent on the fusion rules. We have the total quantum dimension of the system, which is the arithmetic average of the quantum dimension. It's given by that. So if you know the dA, you know capital D. And this ratio has to be taken to the power 2 minus 2g, where g is the genus of the surface. So here I only consider compact orientable surface, which has a genus G, so it will be G equals 0 for a sphere, G equals 1 for a torus, etc. And this expression gives you the ground state degeneracy. So as I told you at the very beginning, one of the important features of topologically ordered systems is that the ground state degeneracy depends on the topology of the systems, and that's exactly what you can see. You can see exactly the dependence here. So what is pretty remarkable here, that can be directly seen in this formula, is that if you are on a genus 0 surface, you have a unique ground state, whatever the category is, okay, that it does not depend on Z of C. For G equals 0, you have D naught equal 1, simply because you can see that you have dA to the power 2 divided by D, and since D is simply given by that, this is equal to 1. Okay, so you have to keep in mind that any topologically ordered phase on a surface has a unique ground state. Okay. Now, if you consider your system on a torus or something which has the same topology as a torus, like G equal 1, then the ground state degeneracy will always be given by the number of anions in the Drinfeld center of your input category. Okay, so if you think about the toric code, for instance, you have 4 objects in the output category Z of C, and you have a 4-fold degenerate ground state. But now if you switch to a larger genus surface, G larger than 2, then D naught depends non-trivially on Z of C, because actually you can see that it depends really on the quantum dimensions. In other words, it really depends on the fusion rules of the system. So now if we come back to our initial example, which was Fibonacci, so the input category C had 2 objects, okay, these are the quantum dimensions of these 2 objects, 1 and tau. We can directly, and in this case, easily build the Drinfeld center of the category because it's given by the product of C with its mirror of C bar. So we have 4 objects, okay, which are given here. They can be labeled by these two quantities, 1, 1, 1 tau, tau 1, and tau tau. The quantum dimension of the object of Z of C is simply the product of the quantum dimension of each of the objects, which are given here. And so we know how to compute exactly the ground state degeneracy very easily. Okay, so as I explained, on a torus, we had, on a sphere, sorry, we have a unique ground state. If we are on a torus, we have a 4-fold degenerate ground state. If we are on a 2 torus, we have 25 ground states, and so on and so forth. Okay? And what is really remarkable in this case is that this does not depend on the geometry of the graph. I never told you what is a graph. This is not specific to the honeycomb lattice. You can take any graph you wish. It's a topological phase, so it only depends on the topology of the system. Okay? Right. So now we can wonder what are the excitations of the system. So I told you that if I have a graph like this, the projector PP projects onto the vacuum, which means I have nothing inside my plaquette. But now, the objects of the Drinfeld center will be, the non-trivial objects of the Drinfeld center will be the excitations. Yes? Yeah, I just consider,
Otherwise, if there are defects, then that would...
Absolutely. So for the moment, everything I'm saying is true for any graph, any trivalent graph that I embedded on a compact orientable surface, okay? We can also extend it for non-compact, non-orientable, non-whatever, but for the moment, I give you all that. That's the only constraint. Actually, we need this constraint to define properly the Hilbert space and all that, but then we have all this boundary physics, the interface and all that, so yeah.
These changes can be done? Or?
For non-compact thing, yes, it can be done. Yes, so for instance, you can take a ladder geometry and close it with periodic boundary conditions, so you have nothing on top, nothing below, and in this case, we know also how to do that, because actually a non-compact surface, we can always interpret it in terms of a compact surface on top of which we remove some parts, okay? And so it amounts to make some puncture, and then you have to play what is called surgery for TQF. Yeah. So all the results I will give are, we also have them for non-compact surface, but I want to make things as simple as possible. Right. So the excitations of the model will be given by the non-trivial objects there. So what do I mean by non-trivial? I forgot to mention that for any category, we always have one trivial object, which is called the vacuum, which fuse trivially with any other objects, which braids trivially. So you can think about the vacuum as being like nothing, okay? But you need to add it for consistency in the definition of your category. So the vacuum of the Levin-1 model is given when you have nothing inside the plaquette, but as soon as you have another object than the vacuum, it will be one excitation, it will cost 1, and these are the excitation of the Levin-1 model. And of course, there's something non-trivial that I haven't tell you is how to build the Drinfeld center of the category from the initial input category, okay? So in other words, how to go from here to there. So that's something non-trivial. It's usually done using what is called the Okneanu tube algebra. This is a technical part. I won't discuss it, but we don't really need it for the moment. You just need to know that there is an algorithm to build a Drinfeld center from a given category to this Z of C. Okay. And in this Drinfeld center, there is a lot of objects. So there is a vacuum, which defines the ground state, and other objects. And among those objects, only some of them violate the plaquette constraint. So some of them will live inside the plaquette of my graph here. But there will also be other objects which may violate the vertex constraint. But here, I'm working in the Hilbert space, which fulfills the vertex constraint, okay? So it means that these objects, which belongs to Z of C, I don't consider them inside the spectrum of the model, okay? So I do not consider this object. And the objects which only violate the plaquette constraint, so the PP constraint, PP equal +1, we will call them fluxon. Okay. So here I give you directly the results because it's a bit long to explain to you how to obtain it. So what we have been doing in these two papers is to compute exactly the degeneracy of each energy level of the Levin-1 model for an arbitrary category. Okay. So previously I gave you the result for the ground state degeneracy. Okay. And this is the result for any excited states containing Q excitation. So how can we read it and understand this very simple expression? Because at the end of the day, you can see that it's a bit more complicated than the ground state, but not that much. So here we have a stupid combinatorial factor, which simply tells you where you want to put your Q excitation among your NP plaquette. Okay, so that's easy to understand. And here we have a sum over the objects of the category, the output category over the Drinfeld center. We have the same typical factor that we had for the ground state, so the dA over T to the power 2 minus 2G. And here we have this correcting factor. So this correcting factor is a non-trivial part. It's something which involves, again, the total quantum dimension, the quantum dimension of the object, the number of excitation Q, and here there is a new factor, Na, which is called the internal multiplicity of the particle A in the Drinfeld center, and this quantity is obtained via the tube algebra, okay? So when you go from the initial category to the output category, using this tube algebra, in between, you compute explicitly this integer Na, which are called the multiplicity of the particle, okay? And so this multiplicity, if it equals 0, it directly tells you that A is not a fluxon, so it is not associated to plaquette excitation. So it allows you also to identify what are the plaquette excitations inside the set of objects of the Drinfeld center. So if it's non-zero, it's a fluxon. If it's 0, it's not a fluxon. And it's directly involved in this simple expression of the ground state degeneracy, of the excited state degeneracy. Yes.
Excitation, which is not a flux.
Yes.
But then if I have a single flux equal to 1.
Yes.
Does this give a negative number by some?
No. Because here you have to sum over all possible A.
Okay.
Yes. So even if it's not a fluxon, it will simply give you a contribution with 0 here, but you have to sum over all possible objects. No, this is a positive integer number. It's not directly, don't worry. We checked it. Okay, so that's the expression, and again, it is valid for any arbitrary fusion category as an input. It's valid for any graph, any topology, and we also extend it for non-compact, non-orientable. Okay, so now what can we do once we have the spectrum and the degeneracy? We can compute, so here I just summarized the result for that. So this is the energy spectrum. We have the ground state degeneracy, and now we can compute the partition function. Exactly, so the partition function, it's directly given once we have the degeneracy because the energy is trivial. And we obtained a very, very simple expression for the partition function of the Levin-Wen model at any finite temperature for any finite size system on any genus surface and for any fusion category. Okay, so it depends obviously on the topology. It depends on the system size. This is a finite size expression. We can also study the thermodynamic limit. I will do it right after. And it only depends on the quantum dimension. So if you think about what I told you at the very beginning, I tried to convince you that a fusion category was essentially defined by the set of objects and its fusion rules. Actually, there are much more that should be given to define everything properly. But at the end of the day, these are the only relevant information that appears in the partition function of the system. So, because this is just the fusion rules that are given from the very beginning. Okay, so we have this partition function. So we can compute, for instance, the specific heat per plaquette. We can look at it in the thermodynamical limit. We have this very simple expression, which only involves the total quantum dimension of the Drinfeld center. So you can see it's amazingly simple. And this tells you that there is no finite temperature phase transition in the Levin-Wen model. Okay, so you may say, okay, it's a sort of no-go theorem. Is it really interesting? We will see that we can go slightly beyond that. And I just wanted to mention that this is fully consistent with the famous theorem proved by Matthew Hastings a couple of years ago, which tells you that if you have a Hamiltonian, which is a sum of local commuting projectors in 2 dimensions, and which is topologically ordered at 0 temperature, in the thermodynamical limit, this topological order will be immediately destroyed as soon as you warm up the system. No, it's always true. So 2 things. You mean this result or Hastings' result?
No, Hastings' result, I know it doesn't care.
Okay.
For the countings that you used to establish this, like on the previous slide, I thought you were able to do all the counting because you didn't have...
Absolutely. No, so this is only valid if you satisfy the Gauss law. Okay, so I have no vertex excitations. This is the very next step that we will do in the coming months, and we are currently working on it. So this expression is really what is given in the original Levin-Wenz paper, where they consider this restricted Hilbert space, that's the partition function. Okay, so it's a bit disappointing, but I should say that we knew it since more than 15 years, so far nothing really new. But it's nice because now we can really compute it and see how this topological order is destroyed with a system size. What is more interesting is to look at some observable like Wilson loops. So usually in lattice gate theories, a long time ago, people studied this observable, as many of you know, to understand the confinement of quarks and to find some signatures of what it means to be confined or deconfined for excitations. And here in this field, in topologically quantum phases, that's also an interesting quantity to compute. And again, with this expression of the partition function, we can exactly compute the Wilson loops at finite temperature. So here I give you the result in the thermodynamical limit, but we also have its expression for any finite size system. It becomes especially simple in that case. And what do we see? So here I consider, again, the simplest case where this loop is contractible. So what is a Wilson loop? You have to imagine that you take a pair of onions. So you create a pair of anion, anti-anion, and you annihilate them. So it's a loop around a given contour, which encompasses here m plaquettes. So m is the size of the area of the loop, let's say. And it gives you some information about the rigidity of this loop. So usually there are two main possibilities. Either your Wilson loop goes to 0 when you increase the system size as exponential minus the perimeter of the loop. This is called the perimeter law. And this is a signature of deconfined excitation, or it obeys an area law, and it's a signature of confinement. And so in this case, what we do observe is that this Wilson loops, it decays as an area law, given exactly by this quantity. But here the question is, what is the value of alpha? So this essentially this coefficient, and we identify two possibilities. Either alpha is strictly positive, and this happens when this internal multiplicity is strictly smaller than its quantum dimension, and in that case, it tells you that the anion A are completely confined at finite temperature. And this is essentially why we lose all the topological properties and why we don't have topological order. But there are still some special excitations for which this coefficient alpha equal to 0. And this happens when this coefficient equal 1, which means when NA equal DA. And this is a very special subset of excitations in the Drinfeld center. So we have seen that we have all excitations Z, some of them were fluxons, and among those fluxons, some of them are called the pure fluxons, and these are the fluxons for which the internal multiplicity is exactly equal, to their quantum dimensions. And these pure fluxons, they have these very special properties that they always remain deconfined, even at finite temperature. So that's one of the important results that we obtained here. Okay, so since this workshop has also something to do with entanglement, I'm happy because I should normally be able to skip this slide. You had already a lot of introduction about about entanglement entropy, so you all know what it is, how to define it. But what is important is that usually, as was said in the previous talks, it's important to keep in mind that we have an area law usually for ground state of two-dimensional systems. But when you have topological order at 0 temperature, usually what is important is not the coefficient alpha, which tells you how it scales with the area law, but rather this constant coefficient, which is known as a topological entropy, and which characterizes the topological order that you have in the system. So this quantity has been proposed by this set of two famous papers by Kitaev, Preskill, and Levin and Wen in 2006. But what happens is that if you're interested in finite temperature properties, at finite temperature, your entanglement entropy doesn't scale anymore at an area law, but it scales as a volume law, okay? So it's harder to extract this constant term, and that's why usually at finite temperature, it's rather worse considering the mutual information, which is simply given by this expression, where S is the entanglement entropy. So that's exactly what we did. And we computed this mutual information, and more specifically, the topological part of the mutual information, which again, obey an area law at finite temperature, and we want to extract this constant term, gamma prime. And there is a conjecture in the literature which tells you that this topological mutual information is given by this, expression, where PAR is simply the projector in a given region R of your system, which is actually given by the partition you consider from the very beginning, onto the particle A. Okay, so with the tools we have in hand, we can directly compute also the expectation value of this, and compute the behavior of the topological mutual information as a function of temperature. So since time runs out, I will try to give you the results directly. So here I took another example, like the Ising category. Here are the fusion rules, we have many things. And if you compute this topological entropy, mutual information, sorry, as a function of the inverse temperature, you can see that, okay, when you increase the system size, it goes to the left, okay? So you have this curve, and it takes two limiting values. So when the temperature goes to 0, which means beta goes to infinity, you recover the value expected at 0 temperature for the topological mutual information, which is essentially 2 times the value you expect for the topological entropy. So here you have your -2 log D, you're happy with it. But at finite temperature, you can see that there is a sort of balance between the system size and the temperature. And this is important because previously I told you that topological order is immediately lost when you warm up your system, but this is only true in the thermodynamical limit, okay? So if you have a finite system size, this mutual information tells you that you preserve topological order up to a temperature which depends on the system size. So there is a non-trivial scaling variables, which is given by this quantity, the system size times exponential minus beta, which is a universal, which is the proper scaling variable to put all these curves on top of each other. Okay, so ITOPO is a universal function of these scaling variables, and this tells you up to which point you can go if you have a finite size system, up to which temperature you can go before losing completely the information about topological order. Okay, so again, this had been studied in the toric code long time ago, but here what is nice is that we have the exact expression and we can derive exactly this scaling variable and study how it goes with the system size. Okay, so I will stop here now. I just give you these take-home messages to remind you that we computed the exact degeneracy of the string net model for any category, on any graph, on any surface, any topology, any whatever you wish. There is no phase transition at finite temperature in the thermodynamical limit. We found also this area law for the Wilson loops at any finite temperature, but we also found that for some particles, some special subset of fluxon, this pure fluxon, some of them remain deconfined. This is an important information. We also show that the topological mutual information goes to 0 at finite t, but there is this scaling variable which gives you a finite range of temperature and system size into which you can work. So this is important because, for instance, there are many groups who are trying to engineer this kind of device, and if you think about toric code, like Google is realizing some superconducting qubit systems in which they want to have this anion and work with them, but obviously experimentally they work at finite temperature. But what this tells you is that they cannot work with infinitely large systems, so you will never get an efficient topologically ordered system with 2000 qubits unless you're able to work at very, 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 very low temperature, okay? And that the scaling variables which tells you the balance between both. Okay, so I will stop here and I'm ready for questions. Thank you.
Yeah, I have a very simple question. So isn't the mutual information for pure states directly connected to the Von Neumann entropy?
Yes, so that's what I've shown here very briefly. Yes, it's given by this expression.
Well, I mean, wouldn't it be even simpler? Like if I have a pure state and I'm taking two bipartitions A and B,
yeah,
then the quantum mutual information would just be like the entire state is pure. So S rho AB
So
would just be zero.
if you have a pure state, SR equal SR bar.
Yeah.
Okay. And if you are at 0 temperature, you can also get rid of this.
So the last term is just 0, right?
Yes. Yeah. So it's completely trivial in this case. Yes.
So R and R bar is the same. SR bar.
If you have yes, R bar is a complementary of R. Okay,
Yeah,
so if it's a pure state, it's the same, yes, SR equal SR bar.
So it'll just be twice of the
Exactly, so that's why the topological entropy is given by minus log D, okay? And at zero temperature, the I-topo is given by minus 2 log D.
Yeah, so I couldn't understand why it would give you an advantage to understand scaling at T greater than 0.
Okay, no, the thing is that if you work at finite temperature, it's hard to extract this gamma term from the entropy itself because it does not obey an area law anymore at finite temperature. It obeys a volume law, okay? And so if you are familiar with this, in these two papers, what they really did is to suggest a protocol to extract only this gamma term by some tree partition and subtraction scheme and all that. But now, since you have the volume law, you cannot use this anymore to extract gamma. But you can do it on the mutual information.
But the mutual information should also follow the volume law, right?
No, the mutual information at finite temperature, it obeys a real law. That's the point. Because you subtract this quantity precisely.
Okay, yeah, I'll discuss
later. Yeah, that's a subtle point.
Julien, I have a comment on this point. So the information that you're looking at with this mutual information is now a mixture of classical and quantum.
Yes.
So is there a way of distilling only the quantum part by looking at the equivalent of this with the negativity or something like this, or it's not?
Yes, we could also consider the negativity at finite temperature. It's just more complicated to compute.
Because this will go from a finite value to exactly 0.
Yes, yeah, exactly. But here, actually, the fact that we do not reach 0 at infinite temperature is simply due to the fact that we are working in a restricted Hilbert space.
There is a constraint, and that's a classical
so
information.
these are some restrictions, and there was some previous work by Trept and Maria Hermans who proved that they studied what they call the classical string net model, which is just the infinite temperature string net. So they computed this value, although they didn't properly identify it, but okay, they computed this value, and this is only due to the fact that we have this restriction. So as Joel was saying, if we want to add charges, this value will be 0, actually.
Any other questions?
I had a question about how your scaling law might generalize to the more complicated world of non-projector Hamiltonians, with, many fractional quantum Hall states or something. I mean, do you think it's just n times e to the minus beta times the NEON gap, or is it like?
So this was something very puzzling for me. I just realized very recently, because I'm completely ignorant in experiment, that apparently even in fractional quantum Hall effect, if your system size is too big, you lose anyons. So that's exactly the question you're asking. I can really not promise, I think there is no reason to believe that the scaling variables is completely universal for any systems or anything. I even do know some, there are many things to say about it, but let's say that all these only do concern a Carroll phase. So the very first question is it the same for Carroll phases, for instance? Like if you think like IITF honeycomb model at the isotropic point, you have this Ising phase. Is it the same scaling variables? I don't know the answer. So especially, I don't know if it will scale to the same way for.
I mean, you might think there could be some physical argument, like e to the minus beta would be something about the density of defects.
Absolutely. And here in this case, the anyons do not interact at all. So there will be also some corrections due to the fact that you have interaction between anyons. So I don't believe there's any reason to believe that it will be the same. But I still do believe that it's possible to observe anion in fractional quantum Hall effect. So this certainly means that there is an equilibrium.
Not in the infinite system. No, I think that's physically probably right. It sounds.
Yeah, that's true.
Somebody there?
So, is it possible to have two distinct categories which have isomorphic Drinfeld centers?
That's a good question. So you are talking about Morita equivalence, basically. That's what you mean? So, You don't know. Okay. So what is known is that there exists some categories, okay, like C and C prime, which have the same Drinfeld center. And this is called Morita equivalence. Okay, so two categories are said to be Morita equivalent if they have the same Drinfeld center. That's point one. But now what's interesting is that when you want to compute, for instance, well, let's come back to simple things. When you derive the Drinfeld center of a given category, even if these two categories have the same Drinfeld center, so you want to go from C to Z of C, and then you have another category C prime, okay, which has the same Drinfeld center. So this is equal to Z of C prime. The difference between the two paths will be given by the proper identification of these internal multiplicities. Okay, so that's the way you will distinguish the fact that you started from C or that you started from C prime. And then in this case, the excitation like fluxons, which are of interest in our case, will be given by different value of NAs. Okay, so that's an important point. So at first glance, you may say, okay, only Drinfeld centers matter, okay, but you need one more ingredient, and this ingredient is obtained through this alternate tube algebra, which gives you the construction along the way from C to its Drinfeld center.
So in terms of the data for the theory, like the Drinfeld center is telling you the anion theory, essentially, like what are the fusion rules for that anion theory? So
yes.
Are those NA values telling you the S matrix values?
Yeah, absolutely. Okay. So if you, when you perform this Octanu tube algebra process, so when you go from here to there, at the end of the day, you have the S matrix, you have the T matrix, you have the central charge, well, the topological central charge modulo 8 to be precise, and you have every information about your emerging anion theory. Yes.
Okay, thank you.
Any other questions? Okay, if not, let's thank Julien again.
Thank you.